All right, ladies and gentlemen, boys and girls of all ages. What we have here is a let ln of 1 plus x cubed be the function, and the Maclaurin series for ln of 1 plus x equals that. So all I did is replace the x with x to the third, so the same thing's going to happen on the Maclaurin side, right? So it's simply going to be, use this series to write the first four non-zero terms. So I'd have f of x is equal to x to the third minus x to the sixth over 2 plus x to the ninth over 3 plus x to the 12th over 4 plus dot dot dot. Then with general terms, so I got to go my general term, that's negative 1 to the n plus 1 x to the 3n. Yep, it has to be the same term over n. All right, and that should do the job nicely. Plus dot dot dot. All right, and it has raised convergence for the Maclaurin series is 1. Determine the interval convergence. Show the work that leads to your answer for f of x. Okay, well, so I'm looking at it. If the radius of convergence is 1, that means, well, first of all, where's this thing centered? So I look at this and go, well, there's no x minus 1 in parentheses, no x plus 2, no anything inside parentheses. So bottom line, this thing has to be centered at 0. And if it's centered at 0, then I know from negative 1 to 1 is my interval of convergence. Now, there's a problem with me saying that out loud, because what about the two endpoints? I have to check my two endpoints. So what I'm going to do is I'm going to put negative 1 in there, and I get negative 1 minus negative 1 to the third, 6 becomes a positive 1, so minus 1/2. The next one becomes negative again, right? Because I put a negative 1 in there, I get negative 1 to the ninth. So this becomes minus 1/3, minus 1/4, minus 1/5. That looks familiar. In fact, that's a harmonic series. So by comparison test, I now know that the left-hand bound is negative 1 is in fact divergent. Whoops, so that's a curved bracket. 1 on the other side. Now I got to check 1. So if I plug a 1 in this function, I get 1 minus 1/2 plus 1/3. Did I not pick up a minus? I should have picked up a minus here. This is on me. That should be a minus. So minus 1/4 plus dot dot dot. Once I have that little pattern figured out, I would do a alternating series test, which is simply put, it's going to be that f of n is always greater than a of n is always going to be greater than a of n plus 1, and it's alternating series, and the limit as n approaches infinity of 1 over n, negative 1 to the n, parentheses in front, is going to go to 0, so therefore it is convergent. And so I have negative 1 to put a square bracket on 1, and I'm saving space because I'm going to erase all that in just a second. All right, so I need to erase all that. So that's how you do the first two chunks of this problem. Let's get to C. I stuck the answer to part A over here in nice pretty form, so we'll have it ready for us. Okay, so it says, because that's f of x, right? Okay, so now it says here we want to do f prime of t squared. All right, well, f prime of t squared, the derivative of t squared is going to be take the derivative, so that's going to be a whopping, where's my pen? Here we go. 3x squared minus 6x to the fifth over 2. First four non-zero terms, huh? So plus 9x to the 8th over 3. So minus 12x to the 11th over 4. I didn't do that right. Hold on. No, I did right. Okay, so I'm good. And then I'm going to, that's just f prime of x, and I want to find the derivative at t squared, so I'm going to whop and throw a t squared in there. When I do that, I'm going to get 3t to the 4th minus 3t to the 10th plus 3t 3t to the 16th minus 3t to the 22nd, I believe. I'm going to double check my answer just so I don't be too far off the rails. Okay, so it looks like we're good through there. All right, so the next question is, use the first two non-zero quantities to find g to approximate it for 1. So g is the integral from 0 to x. So here we go. So I'm going to use the first two terms. So that's the integral of f prime of t squared from 0 to x equals dx. And then I'm going to go from 0 to x of 3t to the 4th minus 3t to the 10th dt. All right, so now I'm going to roll a little farther forward. Integrate, raises power by 1, divide by the power I get. I raise power by 1, divide by the power I get. Plus c, but I'm going to go from 0 to x, or I put the x in. If I plug in zeros, everything cancels out. So this would be g of x. What if I want g of 1? All right, I plug a 1 in. So I'm going to get 3/5 minus 3/11, which is 33 minus 15 over 55, or 15, 18, 55ths. All right, that should be good for that problem. I'm going to probably have to clear out, let's see here. Minus series for g is oh, actually, I don't need to clear this up for that. Okay, so show that the approximation in part C must differ from g1 by less than 1/5. Oh, alternating series, right? Beautiful. I was sweating it. Alternating series, but now I know. So now I go find the next term out. The next term out was right about here. That was my 3t to the 16th. So 3t to the 16th. 3t to the 16th, and we integrated it. So that would be 48t to the 17th. No, it wouldn't. It'd be 3 over 17. 3 over 17. So that would be the next term. We integrated, good, and then what we did is we integrated, so we plug a 0, good, so that becomes an x. So that's fine too. Just change it to an x when I integrate it. And then the next line was we plugged in a what? Converted series is converted series. Okay, so this was centered at 0, so we're finding it 1. So this is going to be 3, 1 minus 0 to the 17th over 17. So that's 3/17. So we would argue that, okay, so then we'd say the error is less than 3/17 by my proof, right? Which is less than 1/5. So therefore the error must be less than 1/5 by our ruling. All right, so that's how you do this problem. It's a lovely one and worth it. Okay, so I'm going to hit done.